Okay, so here we have our example arbitrary order discontinuous Galerkin solver. You can see we have the ability to specify not only the number of elements, but the local order of our solution approximation for any particular element. I'm not going to go into as much detail on the overall structure of the solver as I did for the Module 2 example solver, because the structure is very similar in nature compared to that one. Ultimately, we discretize our domain, we set up our initial conditions, we build a stencil that accounts for the semi-discrete system, and we then pass this into our time discretization. In this case, we're applying a RK4, as we discussed, and then we save some portion of this and plot it. It's worth noting that there's a special routine in here to be able to make a nice looking plot, because the Legendre points don't go all the way to the edge of the domain, so we would have disconnected elements, not just discontinuities across adjoining elements, element nodes, but gaps in between, because the most extreme Legendre node doesn't go all the way to the element bound. So let's take a look at how this solver behaves for the case of a fifth order local approximation with 32 elements. So this is a setup that's more or less similar to our linear low order solver, except now we're using, instead of a linear approximation, we're using a fifth order approximation. And we're going to use, again, periodic boundary conditions to investigate the conservativeness of the scheme, and just like we did with our Module 2, we're going to use a sinusoid as our initial condition. So let's take a look at what we get as a result. So as you can see, compared to the linear solver, the root mean square value does not change. This means that we're doing a much better job at conserving our quantity. So the other thing to note is it's very obvious that these elements aren't linear. So we can see this particular element right here clearly is not linear. This is our fifth order shape. So what happens if we were to try to use fairly few elements? So let's say 4 elements. So recall, in the case of the low order solver, 4 elements would give you something that barely worked at all. Let's see how that behaves with a fifth order local approximation. We can see we're still within the display of the this particular quantity. We're still perfectly conservative, and we're only using 4 elements across the entirety of the domain. This is the beauty of having adaptable order refinement. We can get away with fairly few elements. We could potentially, we could try to push our luck and see how we do with only 2 elements. Even with 2 elements, we're not doing great, but we're still far more conservative. 2 elements for linear would give you erroneous results within, perhaps half of a dimensionless second. So the ability to have the adaptability with regards to the order refinement is incredibly powerful. So let's take a look at the behavior of this with other potential initial conditions. So one of the more interesting ones is, let's say, something with a compact support. So this is commonly called a mollifier. So rather than having a periodical function that is defined everywhere within our domain, here we have something with compact support, but is still very smooth by virtue of the formulation of it as a mollifier. So let's see how this behaves. So as we can see, the compact support is pretty good. If we were to inspect, we would like this to be 0 everywhere outside of our bump. And we can see, going up to it, we're very nearly 0. We're not quite machine precision 0. So about 2 elements out, we are beyond the support of the bump. But there is a little bit of smearing in this particular order and number of elements. Now, if we were to increase the number of elements that we have, then we should be able to improve the compact support of our bump. So now let's inspect. So we can see it's still 2 elements away that we're back to more or less compact support, but the difference is because the elements are comparatively smaller, we can be closer to our bump, and therefore it has a more limited compact support. So there's a couple other initial condition functions available that you can play around with. I think it would be very instructive for the interested viewer to play around with the various potential initial conditions or create their own. And what you can do is, for a particular order, plot the convergence as the number of elements increases. And you should see that, especially for smooth functions like our sine function, you should get optimal convergence. And optimal convergence in this sense is 1/2 order less than the order of your spatial discretization. So in this case, if you had an 8th order spatial discretization, you should expect that as you refine the elements, they should reduce the error in your solution approximation as roughly h, where h is the element size, to the 7 1/2 power. For non-smooth functions, this doesn't necessarily hold. And it depends upon the smoothness of the function, if it's not infinitely differentiable. One other thing that would be instructive to look at would be to see, as we saw in Module 2, there's some dependence on the time step for the speed of our local velocity field compared to the size of our element. However, we would expect that potentially the local order of our spatial discretization may also have some effect on the allowable time step, such that one may wish to modify the current Friedrichs-Lewis condition to account for this. And similarly, as with Module 2, you now have all the tools and machinery necessary to create your own solver. So following much the same path as you did in Module 2, I would recommend that you write your own solver from scratch using the techniques learned, as it will be very instructive in terms of implementation details, as well as ensuring that you really have a strong grasp in the applications of the various techniques.